All right, welcome to the Explainer. Today we're skipping the massive data centers and glossy interfaces to trace the actual life of an artificial neural network. We're taking a journey from foundational, abstract mathematics all the way down into the microscopic physical hardware of a silicon microchip. Let's dive right in. To truly wrap our heads around the massive, billion-parameter AI models of today, we have to start small and ask a very grounded question. How do these theoretical concepts of a machine learning actually translate into the physical, microscopic wiring of a computer chip? If we can understand how a network learns to solve one single tiny logic puzzle in software, and then how engineers hardwire that exact solution into silicon, we unlock the fundamental blueprint for all modern AI hardware. Think of the perceptron as the fundamental atom of AI. It's incredibly elegant because it's just so simple. You have binary inputs coming in from the left, let's call them x1 and x2. Each connection has a specific weight assigned to it, which dictates how important that input is. We also add a bias, which acts as a sort of baseline threshold. The neuron calculates the sum of these weighted inputs and the bias, and then passes it through an activation function to make a hard decision. It outputs a simple 0 or a 1. And that's it. That is the literal atom of AI. But of course, a single atom doesn't make a complex organism. To build those massive, sprawling networks, engineers simplify this model by absorbing the bias directly into the neuron itself. This gives us a really clean, stackable building block. Once we do this, we can easily stack networks with distinct structures: an input layer where the data enters, a hidden layer where the complex processing happens, and an output layer that delivers the final decision. So why do we even need those multiple layers? Let's revisit a famous historical hurdle in computer science to find out. Say we want our AI to act as a basic logic gate. A single perceptron can very easily be trained to solve the logic of an AND gate. But historically, when early researchers tried to use a single perceptron to solve an XOR gate, an exclusive OR gate, where the output is only 1 if the inputs are different, it completely failed. This infamous failure, known as the XOR problem, literally stalled AI research for years. Conceptually, it's pretty easy to see exactly why NAND is a mathematical breeze for a single neuron. If we plot the NAND truth table on a simple graph, you get dark circles representing a 0 output and yellow circles representing a 1 output. A single perceptron essentially works by drawing a single, straight decision line across this graph. Because all the yellow ones are clustered together on one side and the single dark 0 is sitting by itself on the other, we can easily slice a straight line right between them. In math, this is called linear separability. But XOR? That's a whole different beast. If you plot XOR on the exact same kind of graph, the 1s and 0s are situated diagonally right across from each other. Grab a mental pencil and try to draw one single straight line that puts both yellow circles on one side and both dark circles on the other. You can't. It is mathematically impossible. A single perceptron is structurally incapable of solving this logic because it can only draw one straight line. Enter the hero of our story, the multi-layer perceptron, or MLP. By simply introducing a hidden layer of neurons situated between our input nodes and our final output node, we completely change the math. We are effectively adding a whole new dimension of problem-solving power. Instead of one neuron blindly drawing one line, we now have an intermediate step that processes the inputs before the final decision is even made. So what is that hidden layer actually doing? Think of it as a mapping function. It takes those stubborn diagonal XOR data points and recalculates their coordinates in a new hidden space. It mathematically folds the space, physically shifting the problem points around, even moving one so it overlaps another. Suddenly, by changing our perspective, our final output neuron can draw a straight line to separate the ones from the zeros. The impossible literally becomes possible just by adding a layer of abstraction. Now, sure, engineers could figure out the perfect weights to solve this by hand, but we want the network to learn it automatically, right? It does this using a brilliant feedback loop known as backpropagation and the delta rule. It happens in 3 steps. First, a forward pass. The network makes a total guess using whatever random weights it currently has. Second, it calculates error, comparing its completely wrong guess to the actual target answer. Third, gradient descent. It mathematically traces that error backwards, nudging the weight of every single connection slightly up or down to minimize that error for next time. It repeats this loop thousands of times. That loop right there, that is the absolute essence of machine learning. When we kick off training at epoch 0, the network is basically hopelessly confused. The weights are completely random, the data points are just clumped together in the middle of the mapping space, and the decision boundary line is way off to the side doing absolutely nothing useful. At this stage, it's just total chaos. But let's fast forward through 2,100 rounds of that feedback loop, which we call epochs. After 2,100 times of guessing, measuring the error, and tweaking those weights, look at the transformation. The hidden layer has learned to map the points outward, spreading them apart. And more importantly, the output neuron has learned to drag its decision boundary line right into the middle of the action. The ones and zeros are finally starting to separate. You are literally watching the machine learn in real time.
By epoch 2800, we hit the sweet spot. The error rate has dropped to near zero. The hidden layer has fully repositioned the data points to the perfect coordinates, and our straight line flawlessly segregates the yellow ones from the dark zeros. The neural network has successfully learned to solve the XOR logic entirely on its own. We now have our final, perfectly tuned decimal weights and biases saved in our software.
All right, moving on to from abstract math to physical hardware. So the software has done its job beautifully, but how on earth do we hardwire those trained decimal weights into rigid silicon logic gates? Enter quantization. Software loves complex, infinite decimal numbers, but physical hardware relies on logic gates that only understand binary ones and zeros. So we translate. First, we take our final trained weights and round them off to 2 decimal points. Then, we convert those rounded decimals into binary format using 2's complement. Finally, we lock them into fixed-point arithmetic. For this specific chip, engineers chose a Q3.2 format, meaning every single weight is stored using exactly 6 bits of physical hardware, 1 bit for the sign, 3 bits for the integer, and 2 bits for the fraction. It's the art of squeezing infinite math into physical silicon constraints.
And here is a ridiculously brilliant hardware trick that saves massive amounts of silicon real estate. In a neural network, you constantly have to multiply inputs by their weights, but physically building a multiplier circuit on a chip takes up a ton of space and power. However, because our inputs for an XOR gate are strictly single-bit binary, they're literally always just a 0 or a 1, engineers realized they don't even need multipliers. Multiplying a weight by 1 just gives you the weight, and multiplying by 0 gives you 0. So they completely replace heavy multiplier circuits with simple, highly efficient multiplexers. A multiplexer is basically just a switch that either lets the weight pass through or blocks it based on the input. It is a massive shortcut for hardware efficiency. We do have one last major hurdle, though. Remember the activation function that actually makes the decision? A sigmoid curve requires complex exponential division, which is an absolute nightmare for basic digital logic gates. So engineers cheat, in the best way possible. They code a piecewise linear approximation in hardware description languages like Verilog. By using simple addition and bit-shifting operations, they can perfectly mimic the behavior of the complex curve, without requiring any of the heavy computational overhead. It's just a wonderfully elegant compromise between theoretical perfection and physical reality. So, we've just successfully traced artificial intelligence from a theoretical math problem on a graph through the epics of automated learning all the way down to hardware multiplexers etched into physical silicon. We've seen exactly how to hardwire a neural network to solve a single XOR gate, but I want to leave you with a staggering thought to take away from this explainer today. This exact same architecture, the layers, the weights, the activation approximations, is the absolute foundation of modern AI. If this beautifully complex choreography is what it takes to solve just one tiny logic puzzle, what limits truly exist when we scale this exact architecture to chips packed with billions of transistors? Thanks for joining this explainer. Catch you next time.